Hey there, welcome back to 2241. Today we're going to talk about the cross product of vectors. I know it looks like we have a lot of formulas here. We'll go through them one at a time. There's really no more than in the vector section 1.2. Let's go ahead and get started with the terms. So we have much fewer of these than before. All right, so the terms that we're going to go over are the cross product, of course, what a determinant is, scalar and vector triple products, and then the terms coplanar and torque. And so we'll see those on the next page. For now, let's look at our formulas. We'll zoom out a little bit and see what we have. So we actually have four objects here. We have the vectors u and v in their coordinate representations, as usual. And then we have these two matrices in their coordinate representations. And these are helpful for computing cross products. This one is more of an example. So let's see how the cross product is actually defined. Now, unfortunately, the cross product is a little bit more complicated. So we have u cross v is equal to this, and this, quote unquote, is a bit of a weird formula. So in the first coordinate, we have u2 v3 minus u3 v2. In the second coordinate, we have u3 v1 minus u1 v3. And in the third coordinate, we have u1 v2 minus u2 v1. Okay, so let's examine this for a second and just note some patterns that might help you remember this formula. And we'll get another formula in a minute that helps you remember it even more. Okay, so what we have is that in the first coordinate, the indices are the two different ones. So 1, and we see coordinates 2 and 3 of u and v. And in what order do we have them? So this is a subtraction, so the order matters. And the first term that is not subtracted has 2 increasing to 3. And then the second term, which is subtracted, has 3 decreasing to 2. And everything is always in the order u, v, u, v, u, v, v. Okay, so let's say that one more time. 1, first position, we have indices 2 and 3, the opposites. And then we have 2 to 3 and 3 down to 2 for plus then minus. All right, so let's see what happens in the second coordinate here. I've marked it minus 2 for a reason. Here we have uv plus minus, except the indices, which are 3 and 1, go in the opposite direction. We have 3 going down to 1, and then 1 going down or going up to 3, as opposed to 2 to 3, and then 3 down to 2. All right, and then same in 3, where we switch back to 1 going up to 2, and then 2 going down to 1. Yeah. Okay, so hopefully that is one way that you can think of this, or that helps you understand this. There is another way that we can think of this so that you don't have to remember that minus sign. And what you can do is draw out the numbers 1, 2, and 3, and then draw some arrows between them. Let me do this in a smaller size. So 1 going to 2, 2 going to 3, and then 3 going to 1. And so these arrows now tell you the order in which you see those first terms. So you're going to start at 2 going to 3, first position still 2, 3. And then you see 2, 3, 1. So let's see, 1, first position, you see 2 and 3. 2, second position, you see 3 and 1. And then 3, third position, you see 1, then 2. And then you just have to remember to swap the order of those indices at the end. So maybe another way to think of it even is let's put some other arrows in here. Maybe we'll put these ones in blue. So these arrows go backwards now. So going forward, you have 1 and you see 2 and 3. And then for the minuses, you have 1 and you see 3, then 2. in blue. For 2, you see 3, then 1 going forward. And then for 2, you see 1, then 3 going backward for the subtraction. And then for 3, you see 1, then 2 going forward. And then also for 3, you see 2, then 1 going backward. So we can mark in yellow as the positive direction and in blue as the negative direction. There we go. So positive, positive, positive. And cross product can be a lot to remember, but that is hopefully helpful for getting that formula down. All right, so here's what else we have. This is going to help us as well for remembering that cross product formula. It actually gives us a little bit less to worry about, but you have to learn matrix determinants to start. So what is a determinant? Well, it's a way of turning a matrix into a number. And these matrices have to be square, so 2 by 2, 3 by 3, 4 by 4, never a 2 by 4 or a 7 by 3 or something like that. They have to have the same dimensions, same numbers of rows and columns. So for a 2 by 2 matrix, it's pretty straightforward. We have A2 with these coordinates, and this is your output. So one way to think of this is that you start up here, go diagonal down there, and then you subtract off, going up here, diagonal down that way. So you can think of this as the forward direction, and this as the backwards direction. This is the positive direction, this is the negative direction. Okay, and then for the indices here, if you haven't seen this before, the way that I've notated this is that the first coordinate represents the row. So this is A11 and A12 in row 1. And then the second coordinate represents the column. So A11 is in the first column and A12 is in the first row, second column. Similarly down here, this is second row, first column, second row, first column, or sorry, second row, second column here. Okay. Now, three-dimensional determinants are a little bit harder. There's more stuff to deal with here. But we still do have a forward direction and a backward direction. And the formula is a little bit easier, or sorry, a little bit harder. But here we have A3 determinant is, all right, we look at the first row, first column, first row, second column, first row, third column. And if your column is even, you get a negative. If your column is odd, you get a positive. And then what do we multiply those by? Well, this is called a minor of the matrix A3. I won't put the definition of that down because it's not super important, but you just need to know that basically what happens is we say, all right, say we're looking at the A11 term right here, and I want to know how to get this matrix, this minor. What we do is we say, all right, highlight A11 and everything in the row and column corresponding to that. Everything in the first row and the first column, highlight it, cross it off. What remains down here, that is the matrix that you put as the determinant factor of that first term over here. So let's do this for A12. Again, A12 has even column coordinate, and so it gets a minus. And then the minor that we should get is cross off that row, cross off that column. We'll do this a little bit bigger. And then the remaining matrix consists of these entries just stuck together in one matrix like that. Okay, same for A13. We do cross the first row off, cross the third column off, and your remainder matrix is what you put in as the determinant factor over here. I wrote this out for the first row. You do not have to do that. you can also do this column as the coefficients here. You can do this row, this row, this column, this column. You just have to remember that whenever you're looking at something like A23 and you want to know which minor to put with that, well, you cross off this row and this column, second row, third column. And then the remainder is what you use as the determinant minor. And then how to determine whether you put pluses or minuses there. Well, okay, if the column is even, another way to think of this is as, all right, look at the sums of these numbers. 1 plus 1 is even, 1 plus 2 is odd. All right, so even numbers or even sums give you a positive value, and odd sums give you a negative in front. 1 plus 2 is 3, it's odd. 2 plus 2 is 4, 1 plus 3 is 4. Those are even, so we get a positive number in front. Okay. That said, these numbers themselves can be negative. So you might end up with a negative in front here, or this canceling out to give you a positive. But the formula itself does positive, negative, positive in that way. Okay, so that's kind of complicated. Do some practice with it. But let's see how this helps us with the cross product. So we can think of the cross product as a determinant of a matrix. Now, it's a bit of a weird matrix because I put some vectors inside of it, but here's what happens. You look at the cross product of U cross V, and that can be computed symbolically as the determinant of this matrix, where you write U and then V in the second and third rows, and then you write your basis vectors up here in the first row. And so now, when you write this out, you have I cross off that column, that row, times the determinant of this little guy. J cross off that column, that row, times the determinant of this little guy, 1s and 3s. K cross off this column and that row, and then times the determinant of 1s and 2s. All right. And then obviously with the plus, minus, plus signs. So that's the cross product. I'm going to skip torque for a second and come back to it. We also have these triple products, these scalar and vector triple products. So the scalar triple product is, all right, take the cross product of two vectors and then dot that with another vector u. And this ends up being equivalent to computing this determinant. There's a reason for that. It's a little bit complicated, so I probably will not go over it until the explanations video. But for now, just remember, all right, determinants are our friend. All right, we also have the vector triple product. And this is, all right, do the same thing, except replace the dot with a cross product there. And in this case, we get u dot w times v, and this is just a regular times because this is a scalar, minus u dot v times w, again, regular multiplication scalar because this is a scalar. And it is important to remember that the cross product here is giving us a vector quantity instead of a scalar like the dot product does. Next up and last in our formulas is the torque. So torque is a physical measure of how much something tends to rotate when you apply a force at a certain position. So think about if you would take a bar or maybe like a tire iron on a lug nut on your car, and if you kick the tire iron, it applies a very large force to loosen the lug nut. If you don't know how that works, maybe look up some YouTube videos of it. All right, next is some properties of the cross product, and this is very important. So we need to know how to do algebra with this guy. So the first properties are all more or less algebraic. here we have that the cross product is not commutative. Note in this big red circle right here, there is a minus in front of the cross product. We can interpret that geometrically in a bit, but for now, just think, all right, this guy I have to be very careful with. I cannot just swap the order when there's a cross product. I have to account for it with a minus sign. All right, the next part is the scalar multiplication. This works just like the dot product. You get to put a scalar multiple inside of either coordinate. It is also distributive, so you get to distribute the cross product across addition, u cross v plus u cross w. This one is a little bit different. This you have to be careful with. So this is sort of like an associative property, except you have different types of multiplication going on here. And it says, all right, well, yeah, you can have associativity, but it's going to cost you swapping the multiplication operators as well. So you get to move the parentheses over, but you got to make this a u cross v instead of a u dot v, and this dot w instead of a cross w. Okay. And then last, this is just our vector triple product formula. I just felt like rewriting it again to emphasize that that's how it looks. This is kind of a complicated formula, and we'll talk about it much later. All right, and then number 6 here is where we start to get into some more geometric properties. All right, so this says that the cross product u and v is orthogonal, perpendicular to the vectors you used to make it, u and v. So in 3 dimensions, you can have a line that is perpendicular to 2 other lines. And that's what this says. The cross product is a way of doing that. Property 7 here is that 2 vectors are parallel if and only if their cross product is equal to 0. We'll see some geometric justification for that as well. Number 8, this is a geometric formula for the norm of the cross product. Remember, the cross product does not give you a scalar. So if we want a geometric formula like this, like we had for the dot product, then we have to take the norm first. And it says, all right, do the same thing as for the dot product, except change the cosine into a sine. All right. And then last is that 9 can be, or 9 is that the norm of the cross product can be interpreted as the area of a parallelogram spanned by the vectors u and v. So if this is the vector u and this is the vector v, then they make a parallelogram, just like the tip to tail rule. And the area of this guy is exactly how big the cross product should be. Okay, so moving on, we have our objectives. Easy, medium, hard as usual. So 1, you should know how to compute u cross v. Now use either the first formula I gave you or the determinant one, doesn't matter. You should know how to compute small matrix determinants, so 2x2s and 3x3s. And this one is actually probably the most important. You should understand that u cross v is a vector and not a scalar. And I will put in a link in the page 1.4 to a website that will help you get some practice with determining when some sort of vector expression, like, I don't know, u cross r times v minus negative a is a vector, a scalar, or nonsense. And it's kind of a fun little game to work through. So I'll put the link in the page for that. So medium next is that you should be able to do algebra comfortably with u cross v. So make sure that you know how to use those properties we just went over. Understand the geometric significance of u cross v. So that's property 9, and what we'll draw some pictures of on the next page. Last is that you should be able to set up and solve geometric problems using u cross v. So if someone describes something to you like, you know, here's a tetrahedron, find its volume or its area or something. There are ways to solve those types of problems using the cross product that make them very, very easy. But the catch is you have to know how to use the cross product, know how to set up the problem. All right, here's our hard ones. Again, these are loftier goals that you should work on throughout the course, but not necessarily that you'll need right now. So you should know how the algebraic properties of U cross V can be understood geometrically. Almost all of those algebraic properties have a geometric interpretation. So you can draw a picture that illustrates why that property is true. And then the second one, there's only two, is that you should be able to set up and solve physical problems using U cross V. So this is problems that involve, torques or any sort of like physical electromagnetism sorts of things. These problems involve cross products, or they can, and they can be difficult to set up because they're not usually described in a way that says you should use vectors for this. You have to look at the problem, read it, and then recognize vectors are useful here, and the cross product is the operation I need to use. So that's going to come with practice, and that's your last hard goal for this section. All right, next up, let's look at our terms. So the terms, the cross product here, here's a picture of what the cross product is doing. So you're given a vector u and a vector v. They're at some angle theta. What does the cross product do? Well, it creates a new vector, this red one, that is perpendicular to u and perpendicular to v. It's orthogonal to both, and you can also think that it is orthogonal to the entire plane containing those two vectors. So that's what the cross product does. And actually, you can use this sort of picture and this idea to understand those properties back on the other page. So that's your hint. All right, here's the determinant. What is a determinant? Well, it's that horrible formula that we saw a second ago. What does it mean? The determinant works like this. So when you have a matrix, call it A, it's got these coordinates in 3 dimensions. And what is it doing? Well, you multiply matrices by other matrices, right? And the idea here is that we can write matrices, or we can write vectors like V, or let's use U since that's what we've been doing, as matrices. So you've got A, this big matrix here, and you've got U, which we can write as a column matrix. And then when you do matrix multiplication here, you do across the first row multiplied by across the column here, across the second row multiplied by across the column, across the third row, across the column, and so on. Hopefully you remember how to do matrix multiplication. You get out a new vector. We'll call this AU1, AU2, AU3. And these are going to be, these coordinates right here are going to be dot products, actually. You can think, all right, first row times first column here, that's a dot product. Multiply coordinates and then add everything together. But what happens is you get out a new vector. So let's say I'm looking at the I vector here, vector along this particular line of the cube. Well, that gets moved somewhere else, and it gets moved maybe to this vector, which points in a slightly different direction and is maybe a little bit shorter. Same thing up here, you have this vertical vector in the k direction. Well, if you multiply it by a, it gets moved. And maybe it gets moved to over here. Slightly different direction, slightly shorter. Maybe it could be longer even. But multiplying by the matrix thus changes all of the vectors in this space, all of the ones that are pointing out from the origin in particular. And thus, when you draw shapes here, you can think of this shape as being the set of all of the tips of these vectors. So all of the vectors that fit inside of this cube make up the cube. And so you multiply all of those vectors, they all shift around in sort of a uniform way, and you get a new shape over here. And so you have this thing. So this shape is actually called a parallelepiped. It is the three-dimensional equivalent of a parallelogram. Let's write that out, actually. It's kind of an ugly word. Parallelepiped. All right, you can think parallel piped or something. And so what is the determinant measuring? It is actually measuring the area, or sorry, the volume of this new shape. So if we assume that this cube is a unit cube, it's got volume 1, then when we apply A to it, we get a new thing, a parallelepiped, and it has a different volume. And that volume is the determinant. Okay. Another way to think of this when this is not a unit cube is that the determinant is the ratio of volumes between the new shape and the old shape. Okay, so that's what the determinant does. I'll skip the scalar triple product and vector triple product for a second. We'll come up here to coplanar. Okay, so here I've drawn some points. We've got P, Q, and R in a 3D coordinate system, and then we've got T sticking out somehow. And then here, P, Q, and R form a triangle. We've got some vectors pointing to P, Q, and R. And I've drawn the plane so that it goes through the origin as well. And T is not contained in that plane. It is, so here's a line perpendicular to T and perpendicular to the triangle and the plane. But all of these vectors, the purple ones and the ones between P, Q, and R, are all in the same plane. That is what it means for vectors to be coplanar. If I were to draw a vector from somewhere in the plane to T, this vector is outside of the plane in blue. So it is not coplanar with any of these vectors. Or I guess with any two of these vectors. So you say, all right, pick two vectors, they make a plane. Pick another vector, is it in the same plane? This one is not. So that's what coplanarity is. All right, last up is torque here. Then we'll talk about the triple products. Move this over a little. So torque is a physical thing, it's physics. So we have some banana-looking shape here, and let's pretend that it's nailed to the wall maybe, but it can still rotate freely. That's what these arrows are telling us. Well, if you come over here and you whack that shape with a hammer on the end, well, I should expect it to rotate if it can. What I've done is I've applied a force at some point on the shape and at some distance away from its center of rotation. And I measure how much it's going to rotate, how much that whack does by saying, all right, how hard did I whack it and how far away from that center did I whack it? Why do I need to worry about how far away? Well, think about what happens if you whack it over here instead. If you were to whack it there, right at the center, this thing is probably not going to rotate very much. It might sort of vibrate a little bit, but it's not going to rotate. Oops, sorry. And so that's why we need to worry about how far away or where the whack happens. We also obviously need to worry about how hard the whack is. Okay, so that is torque. And last but not least, we have our scalar and vector triple products. All right, so we've got kind of a big picture here. Here's the scalar triple product. What is going on here? So let's break this picture down a little bit at a time. Scalar triple product looks something like this. You take two vectors, cross them, and then you dot them with another vector. Okay, one at a time. U, V, and W. These guys are all pointing in crazy directions, but we can look at the cross product of u and v first and see what does that mean geometrically. It means the vector pointing in this direction with a specific length. And then okay, so there's our vector in that direction for the u cross v, and then we dot that with w. And if you remember correctly, given this vector, the dot product measures the area of a parallelogram where you take this vector, you rotate it, and then you say, all right, that parallelogram that I made now gives me, or has some area, and that's what the dot product measures. Well, we already sort of had an area here because u cross v measured the area of this parallelogram. That was the geometric significance of the dot product norm. So if you take that area and then you multiply it, you dot it with this area, then you get, with this length, I should say, you are getting a volume, and that volume is exactly this length times this length, and then times the length of w projected onto here. Okay, so you've got sort of a scaled cube. You take this cube and you move it over a little bit. Well, all right, what's the new volume of the cube? That's what's going on with the scalar triple product. All right, what about the vector triple product? So this one's a little bit harder to understand. It doesn't have as nice of a geometric interpretation. But again, we'll work through it a little bit at a time. Here's u, v, and w. The vector triple product looks something like this or like this. Note that it is also not associative. I've drawn these vectors in different directions. So that, I guess it might be hard to understand where that is. So u, v, then cross w is the yellow one. And then u cross vw is the white one right there. All right, so here's u and v. We cross them and we get u cross v in red right here. And then we take this vector and we cross it with w. What do we get? Well, we get a vector that should be perpendicular to both of these, and that's what this yellow one is. Perpendicular, pointing in that direction, and that is our vector triple product. What do I know about this vector then? Well, it is perpendicular to both of these. If it's perpendicular to u cross v, it has to be in the same plane as u and v themselves. But because it also has to be perpendicular to w, it's got to be in the intersection of two planes, the plane perpendicular to w and the plane perpendicular to u cross v, containing these two. So it's a very specific vector in this plane. If we swap this around and do v cross w first, well, we get a vector in the direction of this guy. And then u crossed with that vector gives us this vector down here. It's got to be perpendicular to those two. So these two are not the same vector, clearly. And the vector triple product does not have the associative property. The cross product does not have that associative property. One other thing that I think I skipped over, just realized that, is that the cross product has an orientation. That's what the non-commutativity, I can't swap the order of this. When I compute the cross product, I think of these as sort of like x and y axes, and then the cross product itself is sort of like where the z-axis should go. So one way to think of this is using the right-hand rule. You curl your fingers from the x-axis towards the y-axis, and then your thumb should point in the direction of u cross v. So again, I can't draw a picture quickly, but take your right hand and have your fingers all point in the direction of U, and then curl those fingers towards the direction of V, and whatever direction your thumb is then pointing is the conventional direction for the cross product. And then also the opposite direction is the conventional direction for V cross U. So you turn your hand around and curl your fingers from V to U, your thumb points in the opposite direction. And that's why this is not commutative. All right, so that is our overview video. It's got our terms, our formulas, and your objectives. Study those a little bit, and then we'll come back and do the exam.